with some 5% probability, then there are two implications. So if it's 5% set in the first place, then you have, and your p-value or the probability of occurrence comes back to be 0.025, then you would reject the null hypothesis because the probability of occurrence is within your 5%, I guess, tolerance, if you will. But if you choose to change the level of significance to 0.01, now all of a sudden your decision changes from being one of rejecting the null hypothesis to one of failing to reject the null hypothesis. So pretty much, long story short, stay with the original plan and do not make any changes during the middle of the game. Okay, do not change the rules in the middle of the game. That's one of the common themes. All right, so then here is the grand old formula that we're going to be using in this chapter. And it's pretty much an old friend from chapter 11 and chapter 14 to some extent, but mostly chapter 11, where you had to go ahead and find the difference between the sample mean and the population mean relative to the standard error or the standard deviation of the sample mean. And I prefer for you guys to enter this in a calculator offset by parentheses so you can do it or perform the calculation all in one step. And of course, it's called the so-called one sample Z statistic. And you will use your calculators today, so be aware of that. That's coming. So when we have some hypothesized value mu naught, then we're looking at how far does our sample mean differ from the population hypothesized mean relative to the standard error. So how far is our sample data different from our guess? So how far are those two quantities or numbers apart relative to standard errors for the sample mean? And we use the so-called one sample Z statistic to figure this out. And we will complete chapter 15 today, get through most of 16, but maybe not. So a couple things really quick, some good housekeeping, if you will. Let's have it such that the alternative here, let's make it a strict inequality, strictly greater than. So that makes things easier for us. In different textbooks, you might see at least in there, but for the most part, you'll see keywords like more than or increased. So a good example is a certain drug has improved the patient's response to some stimulus. Well, your alternative is then that the mean is bigger than some number or larger than some number. So more than, increase, that's good. And then how do we compute our Z values here? Well, we find the probability of some Z-score, remember from this guy. We use this formula to get some Z-score, and then we plug this in here and find the probability of that event. So in this case, we call it a right tail test. There's our Z-score of 0, and then of course we'd have some kind of critical value Z such that anything larger than that critical value is in our so-called rejection region. So like our cutoff point. So I'm willing for you to lie to me this many number of times, but if you lie to me more than that, I'm cutting you off. You're no longer my best friend. That's it. You lie to me less than that? Well, maybe you're having a bad week. Okay? So the rejection region is kind of like the area from which we would any z-scores larger than this cutoff point will lead to rejecting the null hypothesis. So any large values of z-score, values of z. So guess what? If that's the right tail test, then you take the mirror image, if you will, and you have the so-called left tail test. Looks better in your notes. So you use words like less than, and most is a little misleading sometimes. Let's say less than, reduced, arbitrarily smaller values of z. And you get the idea here that you probably have a left tail test. In which case you would say, okay, any values of z that are smaller than my cutoff point from the, that's below the mean, I guess you could say. So let's say you have some kind of supplement that reduces weight gain, or that you measure how much weight loss, I guess you could have. Then you look at some z-score. If it's arbitrarily small, negative, below some negative score, then yeah, you would say I have enough evidence to reject the null hypothesis. In this case, this will be a rejection region here. This textbook does not emphasize rejection regions, unlike previous textbooks I've worked with, so I will not go into too much detail, but I think the concept is still pretty relevant. For a large values of z, you reject one way, small values of z, reject the other way. So words like less than, reduced, fewer than, you get the idea, okay? And the p-value, let's see here. If I call this guy z-test, let's be clear about this. Let's give it a nice purple. Z-test is right there. And here's my z-test here. Then if my z-test statistic is already in the rejection region, I'm going to think I'll reject the null hypothesis. But the p-value is a probability of getting a z-score, in this case smaller than z-test, which is the purple region. So in this case, the probability of getting a z-score as extreme as the one I've received is so small that the null hypothesis cannot be true, or my data is flawed. And we'll go through an example here later on. So you have a left tail test this way for you guys. You have a right tail test. And guess what? You have a two-tail test. All right? So you have here, and how ironic, the word different is, I'm different. Yeah, I'm different. All right, so the word different is in there as an example of a hint to use two-tailed, okay? Or is not equal to. So the null hypothesis is h naught mu equals some number. In this case, the alternative is mu does not equal to some number. And as you get it, well, because it's a two-tailed test, we're not quite sure. We may observe we're leaving ourselves room in case we have arbitrarily large values of z or arbitrarily small values of z as far as our test statistic is concerned. So we have two options. We have two tails. We have two options, or two rejection regions. And in this case, let's do it. Two times the probability of z bigger than some z test statistic. So if my z test statistic was here, my z test statistic is there, then I want to find the probability of being out in that region, but because it's a two-tailed test, I have to double that probability. So I made the allowance for two options. Do the mirror image over here, in which case you'd find the p-value is equal to 2 times the probability of getting a z-score larger than your z-test statistic, which is what I have up front. But use your knowledge of symmetry, right? So if you can find this area in your chart, and you must find the area below some z-score as well, then you just double because it's symmetric. Like I said before, get out your calculators. So here we go. You have a random sample of 178 students. They have a sample average of 5.31 drinks per session, okay? And we'll say that the standard deviation is 2.98. Is this evidence that the average amount of drinks per session for college students is different from our original estimate? And everybody, our original estimate was 5, right? Okay. So remember way back when, like on Wednesday, we guessed that maybe, just maybe, the typical person has about 5 drinks. I collect some data, I get 5.31. In your opinion, does that sound like enough evidence to reject the null hypothesis? I mean, you know, I don't know. You know, maybe not, but we're going to go through the test anyway. Because you're thinking in your head, and I saw some of you thinking, or at least it looked like you were thinking. You're thinking like 5.31 and 5. You know, practically, is that a big difference? Maybe not. Okay? So let's go through the test anyway, right? So we'll use some words, some letters you guys know. IDK. Now my guess was 4.5. So what we're going to do is change this around a little bit here. And you guys would write, the first thing you want to do is set up your hypothesis or your plan. So I guess 4.5. What do I know? So let's just use your data, right? Suppose it was 5, or suppose it's not 5. Here is our null. Here is our so-called alternative. And you have 3 conditions that you want to check first of all. First thing you want to check is, do you have a random sample? I think somewhere in the problem, and you guys have it in front of you, you see the words random sample kind of right next to each other. Random sample of 178 college students. Do we have a small enough sample, or conversely, do we have a large enough population? Well, the population of all college students is definitely larger than 20 times the sample size, so that's no problem there. And then, of course, do we have a large enough sample? Yes, we're even told that it follows a normal distribution, okay? And we can use T. We don't know about T just yet. We'll just we'll just leave it like that. So this last sentence should be, however, the sample size is bigger than 148. Sample size of 178 is bigger than 140. So we can apply the central limit theorem from chapter 11. There is a distribution called the T distribution that we'll learn about in chapter 18. For right now, we'll just roll with the good old central limit theorem. So give yourself plenty of room. On your notes, I kind of gave you at least half a page to kind of jot information in there because that'll be helpful for you in the future. And then, of course, you see the steps in the calculator that you're going to use as well. So this is all kind of the plan. Do we have the conditions to kind of get the test started? Sure. So far, the answer is yes, we do. And for good measure, let's make sure that we say we're going to do the test at alpha equals 0.05. That's probably a standard kind of thing to do. So that's the hypothesis, that's the plan. Next step is to use the test statistic. And the test statistic for us was z equal to x bar minus the mu naught standard deviation radical n. So in other words, how far is our sample mean away from what we thought it would be? The sample mean was 5.31. We guessed 5, so we're kind of in the ballpark. The standard deviation was 2.98. Radical 178, I believe. And we just put it in the calculator. So parentheses. I get 1.39. A z-score of 1.39. That sounds good to you? Okay, good. Now, that's not me calling birds, right? So that's just me kind of going back in time. So way back when you had the 68, 95, 99.7 rule. Does a z-score of 1.39 seem arbitrarily unusual? No. 3.91? Yes. 9.31? Yes. 1.39? Not so much. So to go back to our old work here, do we have a two-tail test? Yes, we have a two-tail test. I'm going to guess off the top of my head that our case of 1.31 is not necessarily big enough in our critical region. This is my guess. So if I had to take a guess, I'd say it's probably way back here from a couple days ago. Probably somewhere in that green range. Maybe it's in the orange, but it's not in the red. That's my guess. So it's a likely value. Okay, let's fast forward. So in other words, if I took another sample of 178 people, the sample mean could be 5.29 or 5.10 or 5.40, but it's still in the neighborhood of 5, which is our guess, which is what our classmates gave us. So 1.39 is our test statistic. I'll call this Z sub test. .39. Now, the p-value is this character. We'll use purple for p from now on. Here's 0. Here's 1.39. Okay. and we had a two-sided test. So I need to find the area larger than 1.39, but on the flip side, I have to find the area smaller than negative 1.39 as well. So the p-value for a two-sided test is the probability of getting a z-score larger than my z-test. Then I gotta double that, right, because it's two-sided. 2 times the probability of getting a z-score bigger than 1.39. I guess it's even easier. You could find the area less than negative 1.39 and then just double that. That's one way of doing it as well. And I'll go to the z-chart. Okay, so we'll work this out. The chance of getting a z-score less than negative 1.39 is 0.0823. Well, guess what? Use your math here, use your conceptual knowledge. If that's the area from the chart of being less than negative 1.39, then conversely, the area being larger than a positive 1.39 is 0.0823 as well. So I'm going to say that that's going to be 2 times 0.0823, which is 1646. So in the world of unlikely, likely, extremely unlikely, the chance of this happening, the chance of getting a data value of 5.31 for the mean with a guess of 5 is about 16.5% chance. So that seems pretty likely for our purposes. And now we have to do a conclusion. Okay, so, well, when I did it with 4.5, it was enough evidence. Okay, we'll come back to that. In our case, the p-value of what, 1646 exceeded 0.05, which is the significance level. So anything higher than 5% is unlikely, but not weird, right? Not enough to cause us to reject the null hypothesis. Less than 5%, extremely unlikely, get the null hypothesis out of here. So the p-value is bigger than 0.05, so we will fail to reject the null hypothesis. And you remember you had this. Mu equals to 5. Mu does not equal 5. So then I would say there is not enough evidence at the 0.05 level of significance. Average number of drinks per session. is different from 5. Okay, so we're kind of being technical here, but we're doing a little bit of math or statistical doublespeak, if you will. There is not enough evidence to conclude that it's different. From a practical layman's terms perspective, we're pretty much saying that the average is probably right around 5. Okay? If there's not enough evidence to say it's different from 5, then guess what? It's more or less in the ballpark of 5. Now, so what we're going to do is use the calculator to go through the same process, and then what we'll also do is compare it to my guess of 4.5. So, on your mark, get set, get out your calculators. We'll call this Baker case. And we'll call it our case. So according to your steps, they're right there in front of you. You want to go turn the calculator on. You want to go stat, grapevine over to tests, and it's the first thing you see. So before you had to scroll down to the intervals, now you go straight to the test. Okay, yes. So enter the hypothesized value. In this case, for us, it was 5. The population standard deviation was 2.98. The sample mean of 5.31. 178 people. And then do we do not equal to, less than, or greater than? Not equal to, exactly, because that's what we had a two-sided test. And then I choose to go with calculate. Oh my goodness, you've been holding out on this. Okay, so from the calculator, I get this. Let's call it our case. In our case, I get a z-test of 1.39-ish. I get a p, which is the p-value, 1652. What did I say? 1646. So again, the calculator is more precise than the table, because the calculator is finding the area bigger than a z-score of 1.387891228 and then doubling that. We just chose 1.39, I guess. So let's see here. And then it gives you the sample mean and the sample size. So in our case, we did a test for what? Not equal to 5, that's right. There we go. So that's pretty much the same information that we had. Same z-test statistic, similar z-test statistic, and similar p-value, but the same conclusion, right? You say you'd still fail to reject the null hypothesis, which is pretty much saying we're not going to say except. We'll say mu is about equal to 5. Now, let's go ahead and, since I was so staunch on using that 4.5, let's go with Baker. Baker's example, we'll put that in blue since I'm sad. So say Baker. And in my case, I thought it was around 4.5. So then the alternative is mu not equal to 4.5. So you guys should be thinking already in your heads, right? If the mean value of 5, and we have a sample mean of 5.31, well, 4.5 is further from 5.31 than 5 was. So we should have a smaller p-value, and we should have a larger test statistic. Going back in time, we should be with 5.31 and 4.5, we should be further out in the tails with smaller probabilities. Now we could go through this step by step the old-fashioned way. No. Let's go and use the calculator. So in the calculator, everything's already typed in. Stat, test, z-test. I'll change the hypothesized value to 4.5. And everything else stays the same. Okay? Someone read off your results, please. Raise your hand. Read them off. Yes? All right. So the z-test statistic is 3.626. I'm with you. Go ahead. Okay, so you guys all know scientific notation. It says e negative 4. You take one less than that integer. That's the number of zeros behind the decimal. So e negative 4 means I have a decimal, 1, 2, 3 zeros, and a what? 287. Okay, so I'm running out of room. 29. Okay. For all practical purposes, anytime that you have a p-value e negative 5, e negative 6, e negative 7, etc., that direction, let's just call it 0, right? Let's just call it what it is. When you have e negative 4, we'll play around with it and call it like three zeros and a 3 or 2 nines. So that's okay. So thank you very much. What else does it give? It gives you the same mean, the same sample size. So, but look at the decision, right? In this case, we'll do a dark green. The p-value is 0.00029. So the probability that I observed data of 5.31 for the mean, if the true average was 4.5, the chance for that to be true is about 1, 2, 3 in 10,000. Very small probability. So in this case, because the p-value is smaller than alpha, I would actually reject the null hypothesis. And then therefore, the mean does not equal 4.5. And that's pretty much what I was saying back here. There's enough evidence to conclude the average number of drinks is different from my guess. Let's be clear about that. My incorrect guess of 4.5. Okay, so that's one of the cool things about the calculator. You can kind of get right through all the calculations and talk about interpretation straight away. JMP does the same thing, but you don't have your JMP software at your fingertips mostly. Next. Okay, so here's the process here, and you have a sheet that's kind of like a general template for how to solve hypothesis tests in chapter 15 and beyond. These are the 4 blanks that you want to substitute in. You want to state what it is you're looking for, what is your plan, are you going to solve it, and the conclusion. So again, to be explicit, what is the question that we're looking for, what's our process, do some kind of calculations, and provide a conclusion. But everything else kind of follows that sheet. So you can theoretically use that same sheet of paper for all your homework problems, all your quizzes. So leave that one blank as like the guide. Okay, so then let's go through it. What is the practical question that requires a test? That's the first part. Second part is the plan, the parameter, the background information, the null hypothesis, the alternative, significance level, so forth. So we did state, plan. Then when you solve it, okay, well, do you have what kind of conditions are in place? Find the test statistic and the p-value. And then the conclusion is we're going to reject or fail to reject, and then try to explain it in a practical kind of way. And here we go with a grand old example on the back page. Recall that IQ scores from chapter 14 follow a normal distribution with a standard deviation of 15. People from affluent communities have IQ scores above 100 as your guess. You have a random sample of 35 adults or residents from an affluent community. Their average IQ score is 112, and then of course A equals 0.05 or alpha equals 0.05. So is there enough evidence to support your claim at the 0.05 level? Here we go. We're going to apply that same four-step process to this problem right here. So the first thing I want to think about is, do persons from affluent communities have, we'll say, average IQ scores that are above 100? That's probably the best way of describing it. So is their average IQ score above 100? And theoretically, the average person's IQ score is 100, so are they above that? And then I tend to do this part. We already we already said that. Verbally, we have it up here. That's no problem. But then what I'm going to say mathematically, that basically means that the mean for the population is above 100. So what you're doing is taking this, all these words in English, converting it to mathematics. Because mathematics is what you're going to do all the calculations in that language, I guess you could say. So there's the verbal statement. There's how you view it mathematically, if you will. So you're going to solve, right? Or state, excuse me. State what's going on. Now the plan. If mu is the average IQ score for persons from affluent communities, then part B lists the information that's provided. So the sample size is 35. The sample mean is 112. Putting this in there. The population standard deviation was 15, I believe. Yep. So again, I'm just using the plan part to organize all of the information. The null hypothesis for this class, the null will always be equal to some hypothesized value. So if this was from the background information, that the mean was bigger than 100, then of course the null will be equal to 100. Level of significance, 0.05. Type of test, right tail. What was the clue for it being a right tail test? Yes? More than, above, that sort of thing. Yep. It is not two-tailed. And so if you have a right tail test, then you have some z critical value, and anything larger than that, and the z critical value has an area of 5% likelihood of being larger than that value. So we're looking for probabilities less than 0.05. Let's see what happens. So that's all set up. Okay, so check the conditions for the test you plan to use. Is it a random sample? Yes. Do we have pretty much a large enough population? Or in other words, is the sample size small enough relative to the population? Yes, how do we spell communities? Okay, there are more than 35 affluent communities. I guess that's, well, it's arbitrarily large, right? Can we use normality? We were informed that the data came from a normal distribution, so that's nice. And then the test statistic, again, using the calculator, you just plug in your steps and go to z-test. And then you get the p-value from that as well. So what I want you guys to do now is go ahead and use your calculator and determine the z-test statistic in this case and the p-value. So go ahead and confirm both of those to be true. The only slight discrepancy I get is a p-value that's 0.12345 1. That's what I pretty much get. And again, like we said a few minutes ago, that's basically 0. Using the table, I just took the area to be 0.0001 because it's off the chart. So the p-value is 0 here. So the probability, if in fact those from affluent communities had an average IQ score of 100, then the chance of getting a sample of 35 to have a mean of 112 is almost impossible. So either my data is wrong or my hypothesis is wrong. And in this case, I'm going to say that I'm going to reject my initial hypothesis and say there's enough evidence at the alpha equals 0.05 level to conclude that persons from affluent communities have above average IQ scores, we'll say IE, have an average IQ score above 100. On a test or a midterm or a final, I tend to scaffold through the exercises. So I'll kind of ask part A, part B, part C, part D, like that. The homework just kind of asks the question, is there enough evidence? Then you have to kind of go through all these steps yourself. But students tend to like more of a piecewise handling of that. Okay, so we have another 5 minutes plus, in which case we'll start chapter 16. I wanted to get a little further than 16, but but maybe not. So give me a second to transition into 16. And I'll post 15 tonight. Okay, so I'm still experimenting with this whole student response system, and I'm going to try something. So we may only start like the first 2 slides of 16, but let me just try this component real quick. All right. Okay, so there's the code, attendance. I don't know. Let's see if this works. Take attendance. It usually gives you like a code you gotta text in there to say that you're here. Okay, so let me hold up. Okay, let's try again. Take attendance. I feel like one of those people who just take attendance. All right, and go. All right, so I guess you text this number, and then you put in like some kind of code 1391, and then that tells them that you're here or not here. Okay, so again, if you are having technical difficulties getting your wireless to work here, let me know about that. If you have financial issues or other concerns, let me know about those as well. But I'm just trying to experiment with this week, and then I'll see who's here or not here. And I'm kind of knowing who some of you guys are. Right? Yes.
So if we haven't bought this yet, there's no point in us texting the number, right?
That's correct, because you may text it on your own phone, but I wouldn't know you're not registered, right?
Right.
But next week or whenever, sure. Okay, so moral to the story: spend $20 less this week on spring break, so you can enjoy the benefits of Top Hat. All right, so guess what? It's time to go. I'll see you. Have a great week. How many of you are flying somewhere for spring break? A few of you? Good. Well, fly safely, drive safely.